Algebra 1, Section 8.3, multiplying powers. Start with a quick example. X to the third times x to the fourth. You should know that x to the third is something that could be written as x times x times x. That's getting multiplied by x to the fourth, which can be written as x times x times x times x. This much represents the x to the third, you understand, and then this much represents the x to the fourth. As I multiply x times x times x times x times x times x times x, you get x to the seventh. This is the definition of powers. So what's the net result there of the problem that we started with? Well, you added the exponents, 3 plus 4. Okay, and if you tried this experiment with different bases and different exponents, they'd have to be the same thing, right? So x and x in this case, or a and a, or z and z, or 2 and 2, or 5,000 and 5,000. If the base is the same, this is the result of powers being multiplied. So that gives us the multiplying powers property. And again, just notice, please, that in this, you have a and a. Both bases do need to be the same number, as they were both x in our first example. And what the property says is that a to the m times a to the n would be equal to a to the m plus n. You add the exponents. So a couple quick examples. 3 to the 8th times 3 to the 5th would be 3 to the 8 plus 5. And 8 plus 5 is 13. This is 3 to the 13th. Now, as soon as I do this, I often will get a question and someone will say, do we have to show the 8 plus 5? No. 3 to the 13th, I know you know that 8 plus 5 is 13, so you can immediately go from the problem to the solution, which is 3 to the 13th. Another question would be, do we have to write it as what the number actually is, 3 to the 13th? And the answer is it depends. And if it's something simple like 2 to the 4th or 5 squared or something like that, absolutely you should write that. 5 squared is 25. You should write the actual number. When it comes to something like 3 to the 13th, which I don't expect you to know, you can just leave it as 3 to the 13th. You would actually have to use a calculator. I don't even know what 3 to the 13th is. I'd have to use a calculator. So leaving that as 3 to the 13th is fine. If it's simpler, you should write what the actual number is. Look at a second example here. X squared times x to the negative 4th would be x to the 2 plus negative 4, or maybe you just say 2 minus 4. And that is x to the negative 2. And hopefully we trained you in section 8.1 to not leave it this way, but rather move it and lose it. So this should be 1 over x squared. This is the best, most simplified answer to the example that was given there. Some examples. It says rewrite each expression using each base only once. So we'll just blow through these here real quick. You've got 7 to the third times 7 squared. The bases are the same number, so yes, we can multiply them, and that would be 7 to the 3 plus 2, which is 5, 7 to the 5th. 4 to the 4th times 4 to the 1st times 4 to the negative 2nd. When there's 3 of them like this, you can just add all the exponents. 4 plus 1 is 5, plus negative 2 would be 3. This is 4 to the 3rd. Okay, now 4 to the 3rd is 64. Maybe that's a little bit of a gray area. For sure, next year we'll make you memorize that one in Algebra 2. So might as well know that now. If you need to use your calculator for right now, that's okay. But one day you will have that one memorized. 4 to the 3rd is 64. Give me the number. Here's an interesting one. 6 to the 8th times 6 to the negative 8th is like saying 6 to the 8 minus 8. Well, 8 minus 8 is 0. Sorry for that flying line there, but that's like saying 6 to the 0, which is 1. 6 to the 8th times 6 to the negative 8th would simplify to 1. And I think now, twice now, we've seen why we needed those concepts in section 8.1 before we do these concepts that are coming after. Next. P to the 2nd times p to the 1, right? There's understood to be a 1 right here, times p to the 5th would be to the p to the 2 plus 1 plus 5. That would be 8. P to the 8th is the answer here. Now, careful on this one. Notice you have a q, a p, and a q, and not only that, but you have numbers that can be multiplied as well. You don't want to over-apply a property here. 2 times 3 times 4, that's multiplication. That's 24. Don't add those, right? They're not exponents. That's not part of the power property. This is the commutative property and associative properties of multiplication, which say you can multiply things in any order. And I'm just multiplying 2, 3, and 4. Some people and even some teachers will rearrange things here. I probably don't think that most of you need to see that. You could, and put the 2, the 3, and the 4 next to each other, put the two q's and their exponents next to each other. But the point being, they could be multiplied in any order. 2 times 3 times 4 is 24. P comes before Q in the alphabet, so the next thing I'll put is P to the third. And then finally Q, and this is Q to the first times Q to the fourth. That would be Q to the fifth, applying the power property. So 24, P to the third, Q to the fifth. Let me emphasize again that alphabetical is the way you should do this. It's not the worst thing if you don't remember to do that and you had 24, Q to the fifth, P to the third, but do try to do that alphabetically. Obviously, when it's A, B, and C, A should come first, B should come second, C should come third. When it's X, Y, Z, X should be first, Y next, and Z. So investigate your alphabet and you'll see that this is the best way to write it. 24, P to the third, Q to the fifth. And then we bring in scientific notation. Now again, these numbers can be multiplied in any order. 3 times 10 to the negative third times 7 times 10 to the negative fifth. Well, you can multiply the 10 and the 7. Now notice I'm pulling those together with that line, but this is not a distributive property situation. This is not a FOIL. FOIL has a plus or a minus sign in this position and a plus or a minus sign here. This is not FOIL. I'm just multiplying those numbers that are alike. 3 times 7 is 21. 10 to the negative third times 10 to the negative fifth would be 10 to the negative 3 plus negative 5, or negative 8. The equivalent here is 21 times 10 to the negative 8. Now they did say to write this in scientific notation. So just like we learned in section 8.2, take 21 down to 2.1, take 10 to the negative 8 up by a factor of 10. I took this one down by a factor of 10, take this one up by a factor of 10. 10 to the negative 8th getting bigger by a factor of 10 would be 10 to the negative 7th. 2.1 times 10 to the negative 7th. And I think we have one more. It says the speed of light is 3 times 10 to the 3 times 10 to the 8th meters per second. If there are 1 times 10 to the negative third kilometers in 1 meter and 3.6 times 10 to the third seconds in 1 hour, find the speed of light in kilometers per hour. Okay, so this is something we did earlier in the year. And here's what you're doing. You've got 3 times 10 to the 8th meters in 1 second. And you're multiplying that by 1 times 10 to the negative third kilometers in 1 meter, and you're multiplying that by 3.6 times 10 to the third seconds in 1 hour. And if you then take a look at the units first and see that you're going to have meters cancel numerator to denominator, seconds cancel numerator to denominator, you will be left with something in kilometers per hour, which is what they asked for. Okay? And then it just comes down to multiplying those numbers. And I'll just do this real quick. 3 times 1 is 3 times 3.6 would be 10.8. If you have to use your calculator on that, that's okay. But I'm multiplying those numbers that are convenient to do so. 3 times 1 times 3.6. That's 10.8. Times 10 to the, and I'm multiplying those powers. 10 to the 8th times 10 to the negative third times 10 to the third. I'm going to add those exponents. Notice that the bases are the same, 10, so I can add the exponents. And 8 plus negative 3 is 5, plus 3 is 8. Okay? And again, now that's in kilometers per hour. And that is a correct number, although it's not in scientific notation. So what would that really be? It would be 1.08 times 10 to the 9th kilometers per hour. And just for fun, I did look that up. And it is, that means that light, based on the circumference of the Earth, light could pass around the Earth 265,000 times in an hour. Thought that was pretty interesting. All right, so that's your answer. I would note that this problem didn't say to provide it in scientific notation, but I did so anyway. For that matter, you could just give us the number, right? All right, good luck on your homework. Thanks for watching and tuning in. We'll talk to you soon.